Well, so uh, we are discussing this some motivations we discussed in the last class. Okay, motivation that why we should study algorithms. Okay, one example I have given, and more of such kind of examples where we are utilizing this concept of these algorithms and its analysis in modern day applications as well. And modern day, this algorithm is not a subject, it's a technology right now. Okay, so you have to remember that thing. So algorithm is this word you should be remembering, that algorithm is not a bare minimum subject. Okay? Algorithm is not a subject right now, not a subject. Okay, but it is a technology. This it is rather a technology. So it is having broader perspective, rather a technology. So that you have to always remember. So that's why you need to study algorithms and you need to study its complexity analysis. Okay. So before going further, one thing I would like to mention, that how many of you I have created the course. Okay, how many of you have registered? Are you being able to register, or some problems or something you are facing? What kind of problem? Acha. Okay, okay, okay. Maybe some permission I have to set again. Maybe it is not by default coming. So today I'll again check, and I'll make sure that maybe by tomorrow you'll be able to register yourself. Okay, so I'll make sure that so actually I was expecting some reply from you, and nobody told me like that. Okay. Actually you could have called me. Okay, or you could have given one email to me. Okay, so if you face any problem, and also another thing is that, say, whenever you will be creating your account in the Moodle, and already I have uploaded the last class video. Okay, so if you see any of the any video of any class is not uploaded, you then and there mail me. One of you, uh, preferably CR, you mail me that that class video is not yet uploaded. So I'll be making sure that it is getting uploaded as soon as possible. Okay, so uh, if by chance I am doing some kind of mistake, you rectify me. Okay, well, so the thing is that so we were dealing with this these algorithms, and we have seen one possible application with this bipartite graph. Okay, bipartite graph. So this is these guys are appearing online in nature. These guys are appearing online, or in a dynamically they are appearing, and I have to take one irrevocable decision. Okay, then and there, when this guy is appearing, I have to assign, if available, say servers are there, or say boys are there, so something like that. That problem we have seen, and with that problem, that problem and its solution, Google, Microsoft, and other big giants are earning a huge amount of profit. Another very good application of this bipartite graph. So this is algorithms. There are many problems which are graph theoretic in nature. Okay, so you haven't studied graph, but you have seen some nodes. So when this when in any problem we are representing it by nodes and edges. So these are edges, okay, these are nodes. Then we can say that, okay, those problems are graph theoretic. Well, so another very important application that of this bipartite graph is this, that say we are having say three nodes here, and maybe these nodes are say companies or say boys, and these are girls, okay. So this type of problem is used in many different applications, and this problem studying this problem in 2012, so this is actually being studied, first studied in economics, and then computer science has taken it as well, okay. So in 2012, because of this, the solution of this problem in 2012, Gale and this Shapley and Roth, so this Shapley and Roth, so they got Nobel Prize in economics, okay. Nobel Prize, can you imagine, Nobel Prize in economics? So we need to study algorithms, and I think if you are serious, one of you may get Nobel Prize in economics, okay? And there is a huge amount of research is going on the border of economics and computer science, okay. That means merging these two fields together, economics and computer science. It's a huge amount of work going on, and basically it is going on in this area called game theory. And maybe fortunately that is my field of research as well, okay. So you see this is a very important applications, important problem, and for which we are having several different applications. If we can think of in an abstract way this problem, I'll be mentioning few of the applications. So the problem is that, well, these are the boys. Say this is the matrimony site, matrimony site one is there, and there are few matrimony sites, they are employing these algorithms nowadays. And more, this is the absolutely modern day application right now. So this is a matrimony site, and they are having boys, set of boys and girls, they should be paired up, okay. So there are matrimony sites, there are dating sites as well, okay. So they are employing these algorithms. This is the Nobel Prize winning algorithm. So the problem is that, okay, these boys may give preferences over these girls. So this is first boy, this is second, this is third, and this is girl A, B, and C, okay. And this boy can give preference over this. Say this first one is giving preference like A over B over C. The second guy is giving the preference like B over C over A, something like this, okay, and so on. And there are this should not be happening in one-sided way. Otherwise, this girl's side might be very angry, okay. They should be having also the chance to choose from the boys, okay. So the girls, this girl is giving preference that she is preferring 2 over 1 over 3. This guy, similarly, this guy say maybe preferring 3 over 1 over 2, something like this. Okay. And now the thing is that we have to match boys with the girls so that everyone will be happy. Okay. Everyone will be happy. So what is the definition of happy? We are not discussing right now, but this is just a motivation. Okay. That means we are having a set of boys, set of girls, and we are giving preferences. Okay. So this you can think of, there are huge amount of that means lots of applications. If we are thinking it in an abstract way, that in this side we are having some nodes, in this sides we are having some nodes. Okay. And this side can give preferences over this side, and this side can give preferences over these sides. Okay. Then we can have several different applications. So one application already we have seen, matrimony sites or dating sites. Another application could be that this side could be schools, this side could be schools, right? This side, and this side could be students. Okay. So schools giving preference over students, student giving preference over school. So this is this is the school choice problem. A huge amount of research work is going on in that area. Okay. MIT, Stanford, every leading universities are working on this. Okay. So this is school to students, and there could be another thing is that these are say NIT students. This side is NIT students, and this side is the company who are coming for the internship. So you are giving preference over the companies, and companies giving preference over you. And this is actually this way. It is not happening in India right now, but from 1951, from 1950s, okay, 1950s, this way the medical students, and there are several companies who can capture these students. So the matching between companies and medical students in USA is happening with this algorithm. Okay. So there are lots of applications. Okay. So there are other problems like kidney exchange, maybe kidney exchange is a killer application. So it may be the case that one-sided preferences may be allowed, such as house allocation problem. Okay. So house that means this side may be the users and this side may be the house. Users are giving preference over a house, and there is maybe it will be little awkward to have the house is giving preference over the users. Okay. So this kidney exchange. So there are patients and donors. Okay. Patients and donors can be matched with this, and this is huge in India. In India, we are not employing this. I don't know why. Okay, still not started in a big way, but this is started in many different European countries and USA as well. Well, so these are some of the modern applications. Okay, some of the modern applications that I am mentioning. Because of some graph problems and some other problems. Okay. So this is showing that we have to study these algorithms. Okay. Okay. So now this we have to study this asymptotic notation. We have to first thing we have to study the problem. The problem is that how to analyze one algorithm. how to analyze one algorithm. How to analyze one algorithm. If you have say you are studying one algorithm, or you have designed one algorithm, then how can you analyze this? Okay, so you listen carefully. Okay, say I might be asking any one of you some questions. Okay, so this is whenever you are attending classes, you please attend seriously, and I'll be noting that who is being able to answer the question, who is not, and based on that also this class assessment marks will be set up. Okay, so it is not the case that only I will be only talking. You should also be talking. Okay, talking with me, right? But you see that we should learn together. That means it is not the case that it's a threat. You should be taking it positively. Okay, this is not a threat. This is a two-way communication I am trying to set. This is not at all a threat. You will be given plenty of chances to rectify yourself. So one question, one day you are not answering, that means you are gone. That is not the case. Okay. So don't take any kind of tension. Okay. Anyway, so this how we can analyze algorithms. Okay. So that is the first thing what we have to look into whenever we are studying algorithms. Okay, because if we don't do that, then there is no point studying algorithm. Okay? Only mechanically understanding the thing is not the study of algorithm. And as I told you that this one book that is called this Ravkaden, Team Ravkaden. Okay. So this Ravkaden book is very important. So this is from this notes is from CLRS. So CLRS, this note is from CLRS book. Okay. And Tim Ravkaden's example also will be taking time and occasion. So Tim Ravkaden, this Algorithms Illuminated. This book, the Kindle edition available, you can purchase. Algorithms Illuminated. So this is these four book series we are having, and everybody should be looking into these books. Okay, for your campus interview also. Okay, if you want to get into Google, want to get into Amazon, say Microsoft. Okay, Microsoft means Microsoft Research, then definitely this Ravkaden's book will be helping. Okay. Okay, so say this. Okay, one page, one blank page I am creating. One blank page. Okay. Say this. Huh? Yes. Why are you asking? I told you, means I am recording. So let me check. Yes, maybe I'm forgetting, then that might be a problem for me. Okay, it's recording. It's recording. Each and every class I'll try to record, and that's a good thing that you have reminded. You should remind. Very often I forget. Because I'll be uploading every video and every lecture notes that I am preparing, so that you can prepare yourself as well. Okay, so say one problem is there. This is an array A. So this array containing some numbers say maybe 10, 25, 1, 9, something like that. Okay. So array of n integers given. So here n equal to 5. So you can think of thousands of numbers in that array. And we have to search one number in this array. Say a number t. We have to search whether this set t equal to, maybe I'm giving 1, or maybe I'm giving 9. And whether this t 9 is present in this array, you have to find out. Okay, so you can write one algorithm for this. So this is from Rough Garden. I have taken. So for I equals to 1 to n, and then you can do if ai equal to t, then return true, so this else returns false. So this is one pseudocode I have written for I equals to 1 to n, and then this if ai. So when I equals to 1, I am searching a1. I am searching a1, and what is that? a1 equal to 10. So is a1, that means 10 equal to t9? No. Then return true. Otherwise we have to go for this return false. I guess it should be from here, this return. Yes. So this CLRS book is assuming that until stated otherwise, the array index will start from 1. Okay, so we will going by that index, that indexing. And if you are familiar with say 0 to n minus 1, then you can write I equals to 0 to n minus 1. So here I am assuming that array index is starting from 1, but that's a good question. Okay, yes, every doubt we should clear. Some doubt maybe I may immediately be solving. Other doubt I have to again go back, and maybe I'll be giving you in later part. Okay, but most of the doubts I think I can clear in the class itself. Okay, so if this is the case, right, you have designed this algorithm, right, and somebody is asking that what is the time complexity of this? What is the time complexity? What is the time complexity of this? So if somebody is asking this question, what is the time complexity, then how can you proceed? Okay, so the thing is that we can have some kind of detailed analysis, which we basically do not do whenever we analyze the time complexity analysis. But at the beginning, if we do that thing, then it might be easier for us to understand what's going on. So line by line, I can take this line, how many times this line being executed, how many times this line being executed. Say this for I equals to say 1, 2, 3. Can anybody say, and something is happening out here? So can anybody say that how many times this statement only will be executed? Will it be 3 times, or will it be 2 times, or will it be 4 times or 5 times? What? Can anybody say? Sorry? No. This I equals to 1 to 3. How many times this statement will be executed? This statement only. How many times? 3 times? Are you sure? 4 times? Why? Why? Yes. So at the last also, it will be coming here, and then I at that time will be 4, and it will be checking whether it is going beyond the range, and then it will not be executing the inner part, right? So this statement alone, if it is 1 to n, then how many times it is getting executed? N plus 1 times. That's good. Very good. And how many times this statement being executed? If ai equals to t, so every time at the worst case, okay, we are talking about at the worst case. So worst case, how many times this is getting executed? So it may so happen that the element I am searching for is at the end of this list. So then this checking will be done n times, right? How many times this statement will be executed? 1 time. If it is true, then it will be definitely being executed 1 time. Return false, how many times? So return is in this. Whenever I am coming out of this, then return false. Okay, this is not with this if. If is this, and then return true. Otherwise, it is not coming out of this for loop. Okay, it is checking all the things, and then it is, if it is thinking that it is not finding any, then it will be returning false. So how many times? 1 time. Okay, so at the last, if it is otherwise, if it is somehow it has found here, then return true, and it will be exiting the loop. Okay, it will not be executed anymore. So now this is n plus 1 time, n time 1 1, and then so this what will be the time complexity in terms of this number of inputs n? So this is n plus 1. We have to add up all the statement cost. N plus 1, n plus 1 plus 1. Okay. So this is 2n plus 3. Very good. Okay, somebody has already pointed out, right? So fn equal to 2n plus 3, that we have got. Fn equal to 2n plus 3, right? So now what we do is we tell that, okay, to have a very nice crisp form of this fn 2n plus 3, we say that it is okay, it is in order of n. Order of n means, so this is 3 means 3 n power 0. So this is n power 1. So this is the highest power of n power 1, and that is actually becoming as the order of n, right? Fn equal to order of n, right? But the thing is that from some other algorithms, the statement cost might be 5n minus 2. Some other algorithm, this might be coming 4n plus 10. Okay, but this fn equal to 5n minus 2, that will also be order of n, and this fn equal to 4n plus 10, that will also be order of n, right? So we can say that anything is in the form of an plus b is boiling down to order of n, okay? Is boiling down to order of n, and depending on a and b, it may so happen that it is coming 2n plus 3 or 5n minus 2. So a is here 5, b is 2, 4n plus 10, and so on, okay? So this is of the form, right? It may so happen that for some other algorithms, it might be coming that it is 3n square plus 2n minus 5. So in that case, we write that this is the highest power n square, it is order of n square, right? But it may so happen that fn might be 4n square plus 10n minus 20. Then also we write that fn equal to order of n square, right? So any form fn equal to an square plus bn minus plus c, that will be in order of n square. So from here we can frame a definition, okay, and that is exactly given here, okay? So you are going back now. So you have got, so this definition is exactly like this. So this is order of Gn equal to a set of function Fn, okay? We have seen that, okay, this order of n equal to 2n plus 3, 4n minus 10, 5n plus 2. So this order of n, Gn is n. So order of n is a set of function Fn. It can be 3n plus 2, it can be 4n plus 5, it can be 7n minus 10, whatever. So it's a set of functions. So that's why it is written, it's a set of function Fn. There exists such that there exist positive constants c and n0 such that this condition getting satisfied for all n greater equals to n0. At this point, maybe it is the definition. We have got the idea that it's a set of function, but all these conditions still not clear to you, okay? So for this I have to create another page, okay? I have to create another page after this, and then you see how this thing is coming up, okay? So fn equal to 2n plus 3. That is that we have got, right? And what we are telling is this is equal to order of n, right? So this is our order of Gn. So n is here Gn, right? So Gn is our n, right? Gn, order of n, okay? So we are telling that this order of Gn, the definition of this is equal to, that is the set of function Fn, and here one function I have got 2n plus 3, such that there exist c and n0, these two constants we are having, so that we are having a condition getting satisfied that Fn is less equal to c of Gn for all n greater equals to n naught. So this is the definition. So now you see this Fn, how this definition is coming into picture. Whenever we are, how this Fn, we have mechanically understood that, well, this is the highest power n, and that's why we are telling it is order of n. That is maybe a mechanical understanding. But now with this definition, we can do this, okay? So Fn equal to 2n plus 3. Then this condition, so 0, this Fn is always positive, okay? Whenever we have prepared one algorithm, then definitely we will have some kind of positive cost associated with it. Okay, so this Fn is greater or equals to 0 but less equal to this C of Gn. So what we can write here is that we can write that this Fn is equal to this 2n plus 3. And can I write that this is less equal to 3n? Can I write that? This is the question. If I can write this, then you see that Fn is less equal to, this is our C and this is our Gn, and then that condition will be satisfied, and then we can say that by definition this Fn is in the order of Gn. Okay, so here Gn is n, so it should be order of n. So how can we argue that 2n plus 3 less equal to 3n? So you see this has to be satisfied for all n greater or equals to n now. Initially it might be the case that 2n plus 3 is not less equal to 3n, but we are dealing with some asymptotic analysis. Okay, so that means whenever we do algorithm analysis, we talk in terms of large n. Okay, large n, right? So we should not be confining ourselves 5 numbers, 6 numbers, something like that. We should be considering this 10,000 numbers. Okay, so this for initially it may be the case. That this is maybe this, say this is our this Gn. So this might be our Gn. Okay, and this Fn might be something like this. Okay, so this could be our Fn, and this is our this Gn, Cgn, right? So this is the point beyond which, this is the n0 point beyond which you see Fn is always less equal to Cgn. Okay, this is Fn is always less equal to Cgn, and thereby the condition getting satisfied. So let us look at this. When n equal to 0, what is the value of this 2n plus 3? 2n plus 3. So that value is coming, this is 0, this is 3. So this is 3. What is the value of 3n? So it is 0. So this condition still not getting satisfied. For n equals to 1, so this will be 5. And this will be 3n, 3. Still not getting satisfied. For n equals to 2, so it will be 4 plus 3, 7, and this is 6. Still not getting satisfied. N equals to 3, so this is 6 plus 9, and this is 9. N equals to 4, this is 8 plus 3, 11, and this is 12. So you see, from here onwards, it is either less equal to, or it is equal to or less. Okay, so this 11 is less than 12. So what we can say, that this condition is getting satisfied for all n greater or equals to, here all n greater or equals to, can you tell me? 3. Okay, that's good. For all n greater or equals to 3, we are having this condition getting satisfied. That is, this is our C, this is our Gn. So we can say, by this definition, we can say that this Fn is equal to this order of n, right? So we have gone by this definition, mathematical definition, and we have got it right as well, right? So what you do is you write the first program, that is the searching an array for an element, right? And you do this in Python. you should be writing this. Okay. So today up to this, if you have any question, you can ask me. Otherwise, we can stop here. But before that, before you leave, I can take your attendance. Okay. Okay. So